In this video, we will go over the first lesson of the last chapter, and this will be focusing on sine law. In the previous chapter, we were solving right triangles with the help of the primary trig ratios, so like the sine ratio, the cosine ratio, and the tangent ratio. Unfortunately, those ratios are only good for solving right triangles. So what if you're not given a right triangle? So those triangles will be called oblique triangles. We need some more trig tools, and that's why we are going to work with the sine law today. So I've already shown you the two versions of the sine law. It's really the same formula. So for example, we have here sine of angle A over A is equal to sine of angle B over B, which is equal to sine of angle C over C. So the uppercase letters are angles, so angle A, angle B, and angle C, and the lowercase are the side lengths. So side A is opposite to A, and same could be said for side B is opposite to angle B, and side C is opposite to angle C. So let's just draw a diagram to help us label. So let's say if this is A, this is B, and this is C, so angle A is here, that means side A is here. And then side B is here, and side C is here. Okay, of course you can take the reciprocal of all three ratios, and they'll still be equal to one another. So we prefer this version of the sine law if we're solving for an angle. Okay, because we want to put our missing variable in the numerator, so easier to solve for. It doesn't matter if you use the other version; it's just a step. And you'll use this version if you want to solve for a length of the or side. Let's do side. Let's say side. Solving for a side of a triangle. Okay, so I'm gonna stop this portion of the video, and then I'll just prove the sine law for you, and then we'll go to the sheet. Okay, so let's try to prove the sine law here. What we have is an acute triangle, which means all the interior angles, angle A, angle B, and angle C, are acute angles. We can prove the sine law working with obtuse triangles as well, but that will require us to use some grade 11 trigonometry. So we're just going to stick with an acute triangle for now. Okay, so we have triangle ABC, and what we are going to do is draw an altitude from vertex A and draw an altitude from vertex C. So this is the same triangle. I just separated it because I didn't want the two altitudes to cause any confusion. Now, I chose to draw an altitude from vertex A and vertex C, but you could easily draw an altitude from vertex B instead of vertex A or vertex C. So just a quick refresher, to draw an altitude, you start from the vertex, and then you join the opposite side at a 90-degree angle. Okay, so what we're going to do is use the altitude from vertex A first, because if you look at the altitude from vertex A, it divides this acute triangle into two right triangles. Okay, and what we're going to do is solve for the length of the altitude from vertex A, which I've labeled as x, using the two right triangles. Okay, so if you use a right triangle on the left here, you'll see that sine B is equal to the ratio of x over c, because opposite over hypotenuse. Now, if you use the right triangle on the right side, you will get sine of c is equal to x over b. Once again, opposite over hypotenuse, because this is the sine ratio. So from the left right triangle, you get sine b equals x over c. From the right triangle on the right, you get sine c equals x over b. So if you rearrange, you'll get x equals c sine b and x equals b sine c. So if x is equal to c sine b and x is equal to b sine c, then guess what? Then c sine b is equal to b sine c. And we're going to rearrange it, and we get sine b over b equals sine c over c. Now, what if we worked with the altitude from vertex C instead? Okay, so once again, if you work with the altitude from vertex C, you're going to divide your acute triangle into two right triangles. Okay, so from the bigger right triangle in this diagram, you can solve for the length of the altitude, which I've labeled as y, using, once again, a sine ratio. So sine of b is equal to y over a, right? Opposite over hypotenuse. And if you look at the smaller right triangle here, sine of a is equal to y over b. Okay, it's exactly the same thing we did with the altitude from vertex A. Now, of course, you can't assume the two altitudes to be the same length. That's why you have different variables here. So I chose x and I chose y. Okay, let's go back down. So based on what I just said, then sine of angle A is equal to y over b. And sine of angle B is equal to y over a, rearrange for y. So y equals b sine A, and y equals a sine b, which means b sine A is equal to a sine b. And if you rearrange that, you get sine A over A, which is equal to sine B over B. Now, hopefully we can fill in this blank. So from the altitude from vertex A, we've developed sine B over B equals sine C over C. From the altitude from vertex C, I get sine A over A equals sine B over B. So can we not conclude the sine law? Okay. I'll let you fill that in yourself. Okay, so hopefully now you understand how we derived the sine law. Okay, so by placing the variable in the numerator, we will save ourselves a step or two. As you've seen from the primary trig ratios, it is always easier to solve for the variable when it is in the numerator. When using a sine law, always remember that you need to complete one of the three ratios, meaning you need to have a side and its opposite angle. Okay. So the last few sentences were very important. So the sine law is composed of three ratios. We're saying these three ratios are equal. So we're not going to use all three ratios. Usually what happens is you're going to have two of the three ratios and you need to complete one of them. Because if you can complete one of these ratios, then you'll be able to solve for the missing side or the missing angle. And in order to complete one of the ratios, you need to know the side, the length of the side, and its opposite angle. Okay? We'll show you scenarios where sine law doesn't work later. Okay. So we'll start off by writing the formula, but yeah, we'll write down the formula for this one. So we're solving for a side length. So I'm actually going to use the a over sine A first. A over sine A, which is equal to b over sine B, which is equal to c over sine C. Okay. So let's fill in everything. So we have a, well, is x, and then sine of 37 degrees, which is equal to, where's b? B, oh, I don't know what side b is. And then sine, I don't know what angle b is either. 15 is side c, so 15, and then sine of 72 degrees. Okay, so like I said, of the three ratios, you only really need to use two of the three ratios. So we're going to use this ratio and this ratio. And this third ratio is perfect because one of them is completed. 15 over sine 72 degrees completed. So let's rewrite that. So x over sine 37 degrees is equal to 15 over sine 72 degrees. So x, you can solve for x by multiplying both sides by sine 37 degrees. And then let your calculator do the work. Now before I solve it, let's take a look at the diagram. Is my expectation that x is going to be greater than 15 meters or less than 15 meters? Hopefully you can agree that it's going to be greater than 15 meters. Sorry, it's going to be less than 15 meters because this angle here is 72 degrees. So if you can imagine, you have to open up, like if you can imagine this angle, you have to open up wider. So that means the side opposite to angle C will be larger. Whereas 37 degrees, it's less than 72 degrees, so you don't have to open as wide. So the greater the opposite angle, the greater the length of the opposite side. So without doing any math, I'm hoping that x is going to be less than 15 meters. And of course it is. So let's say round it to one decimal place. Okay. So over time, I don't need you to write the sine law. I'm just going to label the sides even then, you can get away with not labeling the sides if you want. So I'm just going to jump straight into it. So I know I'm solving for x, so x over sine of the opposite angle. It really helps when you know how to prove the sine law. And then we're going to do, we're working with this angle A and the side A. So it's 8 over sine of 47 degrees. I have a complete ratio. I'm very happy. Once again, we're going to build an expectation here. This answer is going to be greater than 8 centimeters because the angle opposite to angle C, angle C is 110 degrees. It's quite a bit larger than 47 degrees. So side C is going to be larger than 8 centimeters. So we're looking at about 10.3 centimeters. Perfect. Okay. Exactly what we thought it was going to be. All right, let's do a few more questions. Okay, so for example 2, they want us to solve for the missing angle, so no problem. As long as we have a side and its opposite angle, then we'll be able to use a sine law. So I can see from here I have this side and its opposite angle, so I'm feeling great about using the sine law. Sure, we can start by labeling the angles. All right, so we're solving for an angle here, so we're going to use the sine A over A version as opposed to A over sine A. So sine theta over 2 is equal to sine of 60 degrees over 4. Before I do the math, my expectation is that theta is less than 6 degrees because 2 is less than 4. All right, so sine theta equals 2 sine 60 degrees over 4, and then inverse sine all of that, and we should get our angle, which is hopefully going to be less than 6 degrees. $20.6. Well, let's say 25.7. All right, 25.7 degrees. All right, let's see. This time they labeled the angles for us. But what I really want to check is, do I have the side and its opposite angle, a side and its opposite angle? And yes, I have this side, side G, and the angle G. So I'm feeling great. Once again, solve for missing angles. So it's going to be sine of angle F over 17, which is equal to sine of 63 degrees over 20. Now, my expectation is F is very close to angle G, because 17 and 20, this triangle is, yeah, it's going to be pretty close to an equilateral. It's not, obviously not an equilateral, but it should be close. All right, so let's all solve for angle F. Let your calculator do all the work. Don't do any intermediate calculations. Like, I don't really want to know what sine 63 degrees is. I just want to let my calculator do all the work, okay? And it makes your life easier too when you only have to type in at the very end. 49.2 degrees. That's actually a little lesser than what I thought it was going to be. Okay. All right, let's do example 3. So this time we're solving for side C. Now, unfortunately, when I look at triangle ABC and what's given to me, I do not have a side and its opposite angle. So I really want to solve for angle A. Okay, before I begin, I know solving for angle A is imperative because I cannot use a sine law. Okay, let me show you what I mean. Okay, if you try to use a sine law, you'll be stuck. Sine 50A. So if you use a sine law with what's given to you right here, you have half of each of the 3 ratios, and really you cannot progress. Okay, there's nothing I can do to solve for side C. But luckily, if you look at this triangle, I can solve for angle A. Angle A is equal to 180 degrees minus 48 degrees minus 58 degrees, because it's a triangle, right? All three angles, interior angles, have to add up to 180. So 180 minus 48 minus 58, bam, 74 degrees. Beautiful. Now that I have angle A, I have one of the three ratios completed, so I am good to go. I actually put a C at the bottom, but you know what? It's a good example of what extra steps you need to take. So I'm gonna go with that. So since angle A is 74 degrees, so sine of 74 degrees over 68 is equal to, and we want to solve for side C. So we really don't care about this ratio in the middle here. So sine of 48 degrees over C. Okay, so we multiply both sides by lowest common denominator, which is 68C. So we end up with C sine 74 degrees over, or equals to 68 sine 48 degrees. Okay, and then divide both sides by sine 74 degrees, and you're good to go. Alright, let the calculator do the work. $52.6 about. Was that expected? Let's see. So since angle A is 74 degrees, yes, then my expectation is C, whatever the answer is, it has to be less than 68 meters. It's always good to have an expectation of your answer. Alright, let's see, what do we have here? The angle of elevation to the top of the tower is 43 degrees. If you travel 100 meters closer, the angle of elevation becomes 75 degrees. How tall is the tower? Okay, assume the person is 1.5 meters tall. So let's draw some diagrams here, or draw the diagram. I think this is actually very similar to one of the homework questions within the last chapter. Alright, so the initial angle of elevation is 43 degrees. When you walk closer, you have to tilt your head higher, so the angle of elevation becomes 75 degrees. Okay, so far so good, and we're going to assume the tower is perfectly vertical, of course. Alright, let's see. I'm actually going to say this is X here. And then this is H. Okay, so if we can solve for X, we can solve for H, because X plus 1.5 is equal to H, because the person is 1.5 meters tall. Okay. How do I solve for X? I would really like to solve for, if I can imagine this right triangle here, that's basically using the tower, I really want the hypotenuse of that. Because if I use the hypotenuse, I can use one of the ratios to solve for X. We'll decide which ratio in a second, but I really want this. So we're basically reverse engineering. If I want H, to get H, I want X. To get X, I want the hypotenuse of this right triangle. To get this, I can use the sine law. Okay, so how do we do that? So this angle here is 105 degrees because it's the two angles are supplementary. And you know what? Maybe we don't need the angle, but I'm just going to solve for that third angle here. Okay, I'm going to solve for this angle here. So this is 105, this is 43. So let's do the difference. 180 minus 105 minus 43. This is 32 degrees. Okay, what else? You know what? Actually, that was a great idea. Solving for this angle is a good idea because I have the opposite side. Okay, so really you want to cover you want to focus on this triangle over here. All right. So I'm going to just show my work here just so I don't lose any information here. I want to make sure everyone's following along properly. So you know what? I'm gonna show you how I got angle 105. So angle A ACB is equal to 180 degrees minus 75 degrees because the two angles are supplementary. So that's how I know angle ACB is 105 degrees. And I know angle CAB is 180 degrees minus 105 degrees minus 43 degrees. And that's how I got 32 degrees. Okay. All right. I really want this. Oh, I can get it using the sine law. So I'm going to hide that triangle one more time. I can solve for the hypotenuse of the right triangle using the sine law. Let's call this y. Okay. So y over the opposite angle, which is sine of 43 degrees, is equal to 100 over sine of 32 degrees. So y is equal to 100 sine 43 degrees over sine 32 degrees. I know it's very tempting to find out what y is, but we really don't care much about y. Okay, so just leave it alone, and then we'll let the calculator do all the work at the end. Okay, so I want to solve for x. Which ratio? Sine, because it's opposite and hypotenuse. So sine of 75 degrees, and I'm allowed to use a sine ratio because I have a right triangle. So sine of 75 is x over y. I already know what y is, so x is equal to y sine of 75 degrees. And if I have x, I have h, because we said h is x plus 1.5. All right, so now let's punch it in everything. So I'm gonna solve for y first. Okay, and then so that's y times sine 75, and then plus 1.5 to get h, which is 125.8 approximately. Therefore, the tower is approximately 125.8 meters tall. Okay, so that's sine law. You use this when you don't have a right triangle, but be careful. In the next lesson, we're going to look at when the sine law fails us. And we already kind of saw a bit of that with example 3.